Alright, hello and welcome back. Let's finish up these slides, shall we? So, the slide's title is Recursion and Beauty, and the first thing we talked about was recursion, and it was beautiful, was it not? So, last time we finished up talking about new kinds of recursion problems, like something to the power of something else, and even getting into fancier things like divide and conquer algorithms, which are good for sorting, but kind of so-so for adding things, but it was a good example, okay? That is the idea. And now let's get right on into beauty, okay? Not that recursion was not beautiful, just let's try and talk a bit more about it now, okay? So let's get philosophical. What in the world does it mean to be beautiful? And a lot of what beauty has to offer, as far as definitions go, is mostly subjective. So a lot of this section, I mean, I'm going to talk about what people have written down, but it's all their opinions and my opinions on their opinions. So beauty at the end of the day is in the eye of the beholder, right? So this is all going to be opinion-based at the end of the day. So let us get started with some definitions of beauty. So I guess I should say definitions. There are two kinds of beauty. If you go and look it up, there are two schools of thought, let's say. So some people think that something is beautiful, or they define beauty to be when this beautiful thing is like ideal. It is the best of its kind. It's symmetric, like a perfect square, a perfect circle. Those are beautiful because they're symmetric. They are the ideal, okay? They're orderly. Like, oh, how do you define a square? It's got the same side lengths. How do you define a circle? It's everything with the same distance away from a center. It's beautiful, right? It's balanced, it's proportioned, etc. Like, half the reason I like this Helvetica font is because all of these little edges end up in right angles, right? That's beautiful to me, and hopefully to you as well. That is the first definition of beauty. It is objectivity, trying to define it, okay? Trying to take like a one-size-fits-all view and actually define beauty that like transcends somebody's thoughts, okay? This is supposed to be like one definition, a real definition that we can just trust, okay? But I think there's another kind of beauty that you have thought about in your life. Something might be beautiful to you, but not so beautiful to somebody else, right? That's the idea. And so the other kind of beauty is subjective. It is not like we're trying to define beauty and everybody has the same definition. Or so they hope. Everybody has the same definition of objective beauty. Transcends time and space. Objective beauty is that kind. Subjective beauty is the kind that brings you some kind of pleasure. And I think that you can probably think of Mill as well, but actually, believe it or not, Kant was all about subjective kinds of beauty, okay? He took that subjective view, as he just said, that everything that brings a person pleasure is beautiful to them, okay? It doesn't have to be beautiful to other people. So I think Kant and Mill would agree here. And so I guess let me tie beauty and recursion in together, unless you're already convinced, which I hope you are. Let's have some more beautiful examples of recursion. Okay, how about that? So my example for you is fractals, and there are so many of them, and they are wonderful, okay? And let me prove to you that every fractal is recursive, all right? So the idea of fractals they are a graph. You're like graphing something, and that graph is what's called self-similar. So there's the recursive part, okay? It is similar to itself. It has itself inside of itself. That's the idea, okay? And so when you zoom into a fractal, for example, that's when you see yourself again, okay? So I guess the idea is no matter what, you find yourself in the other thing. Like the fancy phrase is like a pebble is self-similar to a boulder, which is slightly bigger, and that boulder is self-similar to a mountain. When does the mountain stop being the pebble, right? That's the philosophical question. So yeah, fractals are just like that. You've probably seen like leaves on a tree, like ferns They all like curl inwards, things like that. Those are fractals. That is the idea. And probably the most famous fractal that you might have heard of is called the Mandelbrot set. Okay? And it looks like this. Maybe you've seen this before. And this GIF up here is showing you what happens when you zoom in. So hopefully that is enjoyable. And I think you can start to see, like, just for a second there, you saw pieces of this rotated, right? That was the idea. It's you keep on zooming in, like forever and ever and ever, even on the outside. Like, take the whole thing in, and then like let's look at just this piece right here. It looks like the bigger thing, right? If you zoom in right here, it looks like the bigger thing. Sorry, you can't see that at all, can you? Isn't that crazy? And if you zoom in there to the front bit, you see it again. You see it again tilted, and so on and so forth forever and ever and ever. That's a fractal. That's cool. It's recursive. It has itself inside of itself, but it's never the same, which is extra cool with this particular fractal. Okay, so that is hopefully something beautiful that you can agree on with me about recursion. You can use it to generate these kinds of fractal things. Okay, so what I'd like to do, just for fun, is to code up this Mandelbrot set. Let me teach you some more about it, and we're actually going to write a program that draws this fancy thing. We'll use the turtle library to do it. Doesn't that sound cool? We're going to do it ourselves. So let's go to the Wikipedia page and study it a bit. All right? So maybe I should zoom in and make it not inverted so that you can read it a bit better. So there we go. The idea of the Mandelbrot set is this is a graph in the complex number space. So instead of, gosh, I don't know if I want to use it here or not. Let's go back to here. So instead of this being x and this being y, in complex numbers, we graph like this. You have the real part on this axis and the imaginary part on this axis. So like the complex number 2 plus 3i, if hopefully complex numbers are coming back to you, is going to actually be a two-dimensional, it's going to be a point on a two-dimensional graph. Okay, this is like the x, this is like the y part. Okay, so we graph imaginary versus real. Isn't that crazy? So with that in mind, we can now define the Mandelbrot set. It's about complex numbers, and complex numbers have fancy properties, right? You can multiply them with other complex numbers, and you get fancy things back. And like the i's sometimes cancel, and you end up with a real number. It's just all cool stuff, right? That's the complex numbers. And so the Mandelbrot set is all about this function right here. Dun dun dun. What happens when starting with z equals 0, you continuously perform this operation on the complex numbers. So it's f subscript c of z, I promise this will make sense in a second, equals z squared plus c. Okay? So you start with 0, and you continuously do this over and over and over again if you just keep on doing this f of c function, starting with 0. Okay? We want to see if that sequence remains bounded. Okay? So the idea is if you repeatedly apply a function, sometimes it gets bigger, sometimes it gets smaller. So here is my first, here's like a starting value. Here's an example. Like x equals 5. And let me apply the function like f of x equals x times 2 to this x. So starting with x equal to 5. Oops. So I'm going to apply this function to it, which means, okay, the first time f of x equals x times 2, right? Then I have 10. And then I apply the function again, which is multiplying its input by 2. So f of x would have been, actually, let's just define it. Define f of x as return x times 2. Yeah. So we start with 5, then we have f of 5. You repeatedly apply the function, f of 5. This is, well, it's going to be 10 now, because that's this. This inner part is 10, times 2 is now 20, right? And then f of 5 is 40. And f of f of f of f of 5 is going to be 80, yeah? Repeatedly apply the function to a starting argument. That's the idea. And I think that you can tell if you keep on applying this function, the number is going to get huge quite quickly. It's going to like double, right? And so this gets real big real fast, and we say it diverges when it gets big real fast, okay? And that's in contrast to, let me write these both for you to see later. In contrast to, how about g of x, a different function, equals x divided by 2. Let's look at that one. Let's repeatedly apply that one. Return x divided by 2. Hey. So if I start with, I don't know, g of, like I start with 20, and then I do g of 20. Oh, now it's 10. g of 20. Oh, now it's 5. And I think that you can see, if I repeatedly apply this, it's going to get closer and closer to 0. Yeah? Smaller and smaller. And this repeated application of the g function to a starting argument, it does not diverge. It stays within a range. It eventually becomes very, very close to 0. So apply it enough times, it'll be less than 1. See that? One more time, actually. So there's a big difference between this function and this function. And it also depends on the value, right? Sometimes. That is the idea. So coming back to here now, it's the idea of you have this function, repeatedly apply it to 0, and see where you get, okay? And at each complex number, because that's what the plus c part. Okay? Repeatedly apply that function, and apparently this is what we end up with. Okay? And we want to keep track of whether or not it remained bounded, because I think it's the black part of this graph is the bounded part, like it comes between 0 or less, stays less than 100 or something, and the outside part is the stuff that goes up and up to infinity. Okay? That's the part that diverges. So that is how we can graph this, and let's see, is there a way, I forget the bounds. I guess we'll just figure out the bounds ourselves. Let's try like 2 and 2 to start, okay? So let's code this. Now we're ready. I think I've explained it enough. So we do have time. I'm excited. The first thing that we need to talk about is nested loops, because nested loops are going to allow us to visit every coordinate on a graph. Okay, and that's very important. So let me talk about this. So just like we can have for I in range 5, and if we were to print I here, you know what it would do, right? Or sorry, not 5, but I. It would print 0, 1, 2, 3, 4. Yeah? That's all well and good. What if I did this, though? Another loop inside the loop for, let's do J. What if I print I, comma J? What would this do? What would it print out? Okay, you can put loops inside of loops, and that's crazy. Let's see what happens. Let's make a new file. And might as well save it on desktop in that folder, and this is lecture 31. Are you ready? So this is going to be, I guess, nested loops.py, and take your guess. What do you think this is going to print? For I in range 5, for J in range 5, print I, comma J. And so this is just going to print out I and then a space and then the value of J as well. Okay, so what do you think this is going to print out? How many lines do you think it's going to print out? Let's try it. Oh man. So look what happens. 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4. Interesting. All the way to 4, 4. 4, 0, 4, 1, 4, 2, 4, 3, 4, 4. Why did it do that? So the secret, the idea is that think of a loop as just code, right? It's just code that needs to be run. This is the entire body, including the loop, of the outer loop. This is the inner loop. It's the body of the outer loop. So every time we have a value of I, this entire thing runs, okay, for each value of I. Run the body, which runs this entire inner thing, okay? So for example, I might start out as 0. That's the first number I is. And then we execute this entire new statement, this entire body of the loop, which includes the loop itself, that goes through some number j. Okay, so j starts out at 0. And then it's going to change j. So it'll print I is 0, j is 0 for the first time, because now it executes its little body. See that? So it'll print 0, 0, and then it'll increment j, because it's working on this loop in here. 0, 1, because it prints I never changed. 0, 2, 0, 3, 0, 4. And then it's done with this loop. And then it can finally come back and do the next iteration of the outer loop. Okay, now I is 1. And j starts over again, of course, being 0. And so we have 1, 1. No, sorry, 1, 0. And then we're working on this inner loop some more. We have 1, 1. Dot, 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 on and on forever, until I is the last one, it's 4, and then we go through this loop 4, 0, 4, 1, 4, 2, 4, 3, and then j is also 4, and that's the last one. Okay? Please yell at me if you didn't catch that. That is, it's a fun little topic. Nested loops. So just remember that you got to do the inner loop, which worries about this j, which is the second thing I print, every time there's a new value of I. So I starts out at 0, we do the whole thing for j. All 5 iterations. Then now I is 1. We do the whole thing for j. Now I is 1, and j goes between 0, 1, 2, 3, and 4. Now I is 2, and j goes between 0, 1, 2, 3, and 4. That's the idea. Okay, we need that, because with this, we travel through every possible number between 0, 0 and 4, 4, right? Every possible combination of 0 through 4 and 0 through 4. Okay, that is quite nice. So nested loops, they try all the possibilities of your numbers that you have. Okay, and so what we'll do for the Mandelbrot set is we'll have to keep track of little pixels, right? Each little pixel will have to determine whether or not we should fill it in or not. Okay, and so if you zoom in, we'll just make little squares, and this will be like, I don't know, this is I equals 0, and this is j equal 1. J equals 0, j equals 2. That's the idea, okay? And this, once we finish that line, we'll start out with I equals 1, j equals 0, j equals 1, j equals 2, okay? So don't worry if you're not catching this just yet. It is going to make a whole lot of sense when I implement it. I can promise you that at least, okay? Because then we'll see it. So that is the idea, and so let's code this up, okay? So we have to make a new file, of course. Let's do that. New file. Let's call it mandelbrot.py. And what we'll do is, I guess we're good with this for now. We'll definitely import turtle. Let us, let's make him super fast and make him a turtle, of course. I think we might even need to make him faster, but we'll get to that in a second. So here is the function again. We are going to figure out what this function does with the starting value. So let's talk about how complex numbers work in Python. There is a built-in function, so you don't have to import anything. It's called complex, and that makes a complex number. First you give it the real part, then you give it the imaginary part. So if I say complex 2, 3, that is 2 plus 3i, and they like to use j. Okay? That's the idea. So this is 4 plus, or 4 minus 5i. Okay? You just say complex, the real part, and the imaginary part. And then you can do math with them. You can say that and you can multiply it by 2. You can multiply it 2 complex numbers by each other. It just knows how to do it all. Okay? See? So we're going to use that to our advantage. Are you ready? So I think that is a good place to start, and eventually we're going to need another function. Okay? So we will get there. So first, let's make this. Let's make this f function, because that's what we're going to need to use to determine whether or not we're in the graph or not. Okay? Whether we converge or diverge. That's what defines this graph. So let's make this function. And might as well call it f still. What if I make this bigger? That'll work. So let's do def f, okay? And it's going to take 2 things, right? It's going to take a complex number and then a z, okay? So some complex number c and then a z. Really takes 2 parameters, you can think of it that way. And it returns, it returns z squared plus c. That's all it does, okay? That's the function f. That's the special one. And we use that to determine whether or not a value, a point on our graph, is either in the Mandelbrot set or outside of it. And we'll color them differently depending on which one it is. Okay? So what we want to do is figure out how big the number we got back is. Okay, so we want to kind of take the absolute value of a complex number, which I think exists somewhere. So let's search for complex. Dun dun dun. I think it's CMath. We might need CMath. Mathematical functions for complex numbers. Is there a absolute value or something like that? It could be math library as well. We'll figure it out together. Let's try the math library. What about the absolute value? Oh, you know what? Absolute value by itself is built in. So let's see if it's up here. And it does the right thing. Yes. There we go. There we go. Yes, if it's a complex number, the magnitude is returned. Okay, cool. So that means I can say abs of a complex number. And it will return me back a regular number. That is the magnitude of a complex number. Okay, that's the idea. That is what we want, because this is a single number that I can compare to see like if it's getting too big, to see if it's diverging, if it gets super huge. Okay, so here's the idea. Let's keep going. So we want to draw pixels on our screen. Okay, we want to try every pixel and draw it. Okay, so let's say for, like, I don't know, x. Let's start with, I want to do it in order. So let's say y in range, let's do, I'm not sure, 200 to negative 201 by negative 1. And then for x in range, this one can be normal, negative 200 to positive 201. And so it's always going to stop. So y goes between negative 200 and positive 200 inclusive, and x will go between also negative 200 and positive 200. So these are the xy values, and I think I want to scale them a little bit. So let's divide them by 200. Okay. So that really our coordinates are between like negative 2, and positive 2, positive 2. Or wait, I think it's just 1 at that point. Let's see if that'll work. Okay, let's try this and see if we can capture the entire thing. If not, we can play with this scale. Okay. So our real coordinate now is going to be x equals, let's say, should I call it new x or just x? let's just say x. X equals x divided by scale, and y equals y divided by scale. And the reason I'm doing this is so that we draw a big screen, okay? We want to draw a big rectangle with the turtle. So really it should be 400 by 400, but our individual points are going to be, okay, this is like -2, +2. And that's the hope. Okay, this will all make more sense when I draw it. And so then, once we have our points, we have to figure out if it's in the graph. And I do think I want to use different numbers now. New x equals new y. Maybe I should say scaled x and scaled y. How about that? That should work. And then we want to figure out if, like we'll pretend we have a function, if it diverges at scaled x and scaled y, then we should do something, okay? That is the hope. Then we want to draw a pixel at the original x and y with a certain color, let's say I don't know, blue, and otherwise we want to just keep it white or something. That's the idea. Okay, so with this in mind, let's make the diverges function and then the draw pixel function. And this is xy, but when we're trying to do the Mandelbrot set stuff, we have to turn this into a complex number. Okay, so we have to make c equals complex xy. That's the idea. And so now we have a complex number that we could apply this f function to a bunch of times and see if it stays bounded or if it goes and gets really large. Okay, so here's the idea. Starting with that, starting with the number 0, let's see if we can repeatedly apply this function and see what we get back. Okay, that is the hope. So z starts out being 0, and let's just do 1,000,000 times. Try to apply f to itself, starting at 0. Let's do it 100 times. Okay, that's the idea. So let's say for I in range 100 times, do z equals f of c comma z. Okay, that's what we'll do. So we repeatedly apply this function, replace z with it, and then do it again and again and again. So it's repeatedly applying f 1,000,000 times to the beginning. Okay, and then we want to see, was this bounded? Okay, let's say it diverges when its absolute value is greater than 100. Okay, so if abs of z is greater than 100, and you know what, I might need to make z a complex number, 0, 0. Let's just do that to be sure. If absolute value of z gets too big, that diverges, we'll say return true. Otherwise, return false. It did not diverge, and it stayed small enough. Okay, we'll pretend that 100 is like infinity. That's the idea. Okay, so this is our diverges function. We keep on repeatedly applying the f, starting at 0, and we see if it got too big. If it did, we say yes, it did diverge. Otherwise, we say no, it did not. And with that, we can draw our pixels. Def draw pixel at a certain xy coordinate. Give it some color. Okay, so at xy, -200, +200, draw a blue square, please. Okay, so let's draw that. And so we have to say turtle dot up, and then turtle dot go to xy, turtle dot pen color, color, and to make the turtle draw, let's just make him go up a tiny bit. y + 1. How about that? Okay. this should draw a very, very tiny pixel with whatever color we gave it. Okay? At least that's the hope. Let's see how badly I've messed it up so far. So we have this F that defines whether or not we're in, with the help of divergence, it defines whether or not we're in the set or outside of the Mandelbrot set. We return true or false depending on whether we are, and that has to do with whether we diverge by repeatedly applying this function. And based on that, we'll either draw a blue or white square. Maybe we should say black. I might have got it inverted as well, but we'll figure it out. Where we go to that location, we change our color to whatever color was passed, and then we move a little bit because moving is what makes the turtle draw things, right? That's at least the hope. So that is all that I think I have. Let's see if it works. Let's see what it does. Look at him go! He's just drawn white things so far. So turtle's going way too slow right now, okay? First of all, we're going to need to make him go a whole lot faster. So let's figure out how to do that, okay? Let's go down, and it could be speed. It could very well be visibility of the turtle. Could be tracer and things like that. But we'll get there as we need to. I think we already have him at fastest, right? Ooh, cool. So we've done it a bit too much already. So it seems like this is getting huge and it stopped the program. So maybe that was too many. 100 was too many. What we can do is perhaps see if it diverged inside of the for loop. If abs z is greater than 100, then right there return true. And if we got all the way down here, we'll just return false because it wasn't ever too big. That's the hope. Okay. So let's see if it continues now while we work on how to make the turtle go faster. That's better. Okay, so we'll see if he's okay. I think he's already at the fastest speed, right? Yeah, so we're going to have to do even more. And I think this has to go down into the tracer bit, if I remember correctly. We've got delay, we've got tracer. Yeah, we want to accelerate the drawing of complex graphics. So, we want to do what? Yeah, so let's try using the tracer and see if we can set it to like a high number, if that'll make it go faster. That'll make the turtle draw things faster, because he's just trucking along, going a little too slow for our purposes. I think if I just give him one number, like let's tell him to draw every 1,000 times, update his screen. Let's rerun him now. Yeah, look at him go, much better. Okay, and I doubt you want to watch me debug because I had the silliest problem. I didn't have this turtle dot down, so he was never actually going to make any marks. Silly me. Okay, so that's fixed now. If we rerun this, I also increased the tracer to make him draw very, very fast. So look at him. You see that little bit of the Mandelbrot set? It's there. Look at it. So, did I get it backwards? Oh, I kind of got it the right way. So, I think we could zoom out a bit more, and it would look better. But look at that. That's the top part. You see it? It is. There's only one way it can be. So yeah, I think if we zoom out a little bit more, we will have more luck. Or we can keep it at the same zoom level, and maybe we can move it. We can increase the size over there. We'll do something, though. We'll make it work. Okay? But that is... it's the Mandelbrot set. Isn't that so cool? Maybe we should make our Y range be wider on the left. I think that's the right idea, right? Let's make it... or sorry, no, the X. Let's make it, I don't know, if this is 0, 0, this is right now -1. Maybe if we make it -1.5-ish, so -300. Let's try that. So that's quite nice. We could set it to 100,000 if we wanted to. Whee. There it goes. And actually, before I forget, when you tell the turtle to like forget to draw a bunch of stuff, at the very end, if he didn't go exactly that many, he won't actually draw the rest. So we have to say turtle.update at the very end. I think that's what we should be doing. So at the very end of all this, we can say turtle.update, I think. But yeah, that's a job for a different time. Let's just enjoy this. Let's watch it finish. Slow and steady. You can make him go. If you decrease this number, you'll actually watch him draw it a bit better. But this is looking good. And my computer is going crazy because this takes a lot of work. Takes a lot of work to do. And so, yeah, there he goes. And so eventually, I think you can take my word for it, it's eventually going to look like this, and depending on how fast it converged, you can change the colors. That's what's happening here. Sometimes it converges very quickly, sometimes it converges very slowly, and that's why it has these cool colors in this picture. So I encourage you to play around with that if you're interested, and that is what will make it all nice and cool. But this is a start. Yeah, this is the Mandelbrot set. We did it. We actually didn't draw it recursively. Even though it's a recursive fractal, we still used a bunch of loops all over the place. Okay, so hopefully that was fun. I think for the sake of my computer right now, if I want to do the slides again, I should stop all this. So try it yourself, though. I'm going to give you this code. So can I stop it? Can I stop it somehow? Can I do restart? Yeah. Okay. My computer's happy again. Let us move on. That was the Mandelbrot set. Wasn't that fun? Okay. Just a few more slides and we're out of here. So you can, of course, do more fractals with recursion or just recursive concepts. Here's one called, I think this was like a German-ish name, so maybe it's the Koch Snowflake. So what you do is you start with a triangle, and then you divide each side into thirds. Okay, here's how you do it. Here's how you compute it. I'm sure there's a way to do this in the turtle library. Maybe somebody's made this. You might want to look into that. And then you like extend out each middle part. Okay, and so you turn it into like the Star of David next. So that's like the first iteration, and then you do it again. You make all these into thirds, and then you extend those middle bits. And so now we have like a ninja star kind of thing. Isn't that cool? And then you can continue that on and on forever, and it makes a cool little snowflake pattern. Okay, so that's the Koch snowflake, and that's just another fractal. You can make it with, you can see the recursive means. You got this little tiny bit right here. See that? Isn't that cool? So that is another example of a fractal, and let me show you some more beautiful math, and that'll be that. So I don't know why this, it doesn't have the hyphen, I promise. So this is called the four-color theorem, which was a very, very cool result back in the day. So let's just read this together. For any separation of a plane into contiguous regions, which means for any map that you can draw, like here's our, I don't know, let's draw the US, contiguous US, dun dun dun, and then there's like Florida over there or something, right? And we can separate these into states. What the four-color theorem says is you only need 4 colors to color any map that is arranged normally, okay? No more than 4 colors are required to color the regions of the map so that no 2 adjacent regions have the same color. So the idea is you only need 4 colors to color in this map so that nobody ever blends into the other person, okay? You only need 4. That is all you ever need. And this was a very hard theorem to prove, surprisingly, okay? So it seems very simple. It's like, okay, yeah, 4 is a nice number. Surely there's a nice, easy proof for that, but there was not. This is, it took some computational effort, actually, okay? So, yeah, that is That is the idea. So that is the point. And this is not the same as like you need to make a map of countries, because you're kind of forced to make Alaska the same color as the US sometimes. For certain countries they have like exclaves and enclaves, and that kind of ruins everything. But if you did like normal states of things, like you separate it in a nice way where there's no rules on anybody, you don't need more than 4 colors. Okay, so this was proved back in 1976 by Kenneth Appel and Wolfgang Haken, I think, using not just their brains, but a computer. And this made it so cool and also very controversial, because how can you trust a computer? There were a ton of configurations of mathematical kinds of little maps, and it took a computer so very long to check all those configurations. So no human could have ever checked them by hand reasonably. So they had to send off that work to a computer, and that's what helped prove this theorem. Okay? And then everybody's happy, and they're like, yeah, that's the proof. We're done, right? And so many people did not trust it, which is weird. Okay? And so I guess the main question is, should we accept a proof done by a computer? Okay? And this has changed over the years. So a lot of mathematicians at the time, they didn't like the proof of the 4-color theorem when it was announced, because they couldn't check it by hand. That's how they proved everything. That's how they made sure nobody was cheating back in the day. Peer review, right? How can you prove that a computer did it right? And there have been a lot of advances in research into like how to make a perfectly correct program. And so a lot of people trust it nowadays, but back in the day, it was not. It was very controversial. Okay, so that's the 4-color theorem that I wanted to tell you about. It's a very famous one. If you study computer science or mathematics, eventually you'll hear it. So here's the first time you've heard it. And then finally, I want to talk to you about a very, very important theorem, probably the most important theorem, I think many people could argue, in computer science. The most important. So it's called the halting problem. And halt here just means stop running. It's like a program. We say that a program halts when it finishes, or we say it terminates. So those are synonyms. A program is done. How do you know if a program's ever going to stop? If it doesn't have an infinite loop. Yeah? That's the idea. So the halting problem tells us that we can actually have some program tell us whether or not another program ever finishes, which is interesting. It ruins a lot of our fun. So let's pretend, here's my proof to you, let's pretend that we had a function that could tell if some other function would eventually stop running. That would be nice, because we've written a lot of infinite loops, especially if you take a future CSCI class. You'll write plenty of them if you haven't already. And so it would be so nice if we made this function, right? Does this function stop running? You give it a function, and it's like, yeah, I can tell you it does, or no, I can tell you it doesn't. So, yeah, that's the idea. Then, let's ruin all of this, and we'll make the following function g, okay, that we'll eventually give to this. So, here's the function g. We are actually calling this function inside of it. No reason we can't. It's just another function. So we say, recursively, kind of, we say, does this function stop running? G itself. We kind of give the function that we're defining to this magical oracle that can tell us if it stops. And if it ever returns the true, like it does stop, we're going to make sure that G doesn't stop, that we don't halt. We're going to loop forever. Okay? Otherwise, if this is a paradox, right? Russell's paradox, if you've heard of it. If the function doesn't stop running and has an infinite loop, if this tells us that it doesn't stop running, we're going to make sure it stops running. We're just going to return 42, and that ends the execution of the g function. It halts. Oh man. Okay? So if this function told us that it halted, we're going to make sure it doesn't halt. We're going to make sure it loops forever. And if we said that this magical function tells us that g doesn't halt, then we're going to make sure that it immediately stops and it returns 42, and so it does halt. So in either case, we proved it wrong. this function can't tell us anything. And so in both cases, we've come up with what's called a contradiction. We've proven the impossible. And so because of this, once we've proven impossible things, like this is impossible, in each case, that proves that our original idea, our original hope, the existence of this, is false. That means we cannot have a function that tells us when another function halts. Okay? So that ruins a lot of our fun in computer science, and it's a fun little proof. Okay? So that is officially all of the concrete information that I have for you in this course. The final week of class is going to be nothing but a review, and so this is the last set of slides. You got through it. You did it. Hopefully that was fun, especially the Mandelbrot thing. I encourage you to try it yourself and to make these pretty colors if you have time. But that's where we'll stop this week, and so next week it will be all about review. Okay? So I will see you then.